Good day, Doctor. Today, we would like to present our project, which is Spaghetti Beam. We are from Group 5 for the subject Mechanics of Material. Before starting for our presentation, I would like to introduce my groupmate, which is Bernard Chua, Jason Tan, Nordayana, Yenny, and me in short.
Okay, let's start our presentation with our project background on the left. We are tasked with design a cylindrical beam measuring exactly 30 centimeter in length and 1.5 centimeter in the thickness. The unique aspect of this experiment is our chosen material. We are building this entirely out of with the uncooked spaghetti. Our purpose is to evaluate how a symmetrical profile distributes internal bending stress and crucially how well it resists deflection right before catastrophic failure occur. To achieve this, we have five main objectives of the project, listed on the right. First of all, we must establish the precise beam geometry. Then, we will execute a destructive bending test together with the empirical data. The, we will using the physical data to generate the shear force diagram and the bending moment diagram. Fourth, we will evaluate the ultimate normal stress denoted by sigma. And finally, we will derive the safety allowable design stress to understand the theoretical safety limits of our spaghetti structure. Now, I would like to introduce the material that we use in our experiment. First of all is spaghetti. We use it to build our beam. Then we use the paper roll with 1.5 cm inner diameter to form a cylindrical shape of the beam. Then we use the tape to attach another part of the beam to make it the DCM. Otherwise, we also use the rubber band to fix the shape of the beam. Last but not least, we use the measuring cup to determine how much of the water that we need to use to crack the beam. So now I would like to pass to Diana.
Assalamualaikum and very good afternoon to Aizudin and my fellow groupmates. My name is Diana and I'm from Group 5. So today I'll be presenting the shape. So our beam shape is in a shape of the beam is like a shape. So as you can see, of 1.5 centimeter, the picture is attached in this slide. Our beam shape is in. So now let us see the video. Of the cracking of the beam. It is 1.5 centimeter and 30 centimeter long. Okay, so now let us move on to the second component, to the cracking of the beam. Okay, so now let's see the preparation of the beam. So first and foremost, we roll a paper to get the shape of the beam to insert the spaghetti into the roll paper. And then we use binding tape to tape the paper. The reason we use paper is because it is light and also easy to get. Okay, and then the beam length is approximately measured 30 centimeter long, and the thickness of inner diameter of the beam measured is 1.5 centimeter. Then we insert the spaghetti into the rolled paper, and then we cut the excess of the spaghetti to get the length that we desired. And then we use two rubber bands to tie up together the part of the spaghetti that had been cut up so that it will stick together. And last but not least, we use binding tape to tighten the spaghetti so that the spaghetti will be more secure and won't fall off.
Now we're going to talk about the analysis of the beam. The beam needs 2000 milliliters of water so that the beam will break. To find the weight of the load, we use the density of the water, which is 1000 kg per meter cube. First off, we convert the 2000 milliliters into the meters cubic. Up After that, we can times it with the density of the water so that we can find 2 kilograms of water. Up next is the weight of the beam. Since the beam is a cylindrical shape, we use the volume of the cylinder to find its volume. After that, we times it with the density of the spaghetti, which is 1.44 gram per centimeter cube. After that, we found out the weight of the beam. Next, to find the total force, we use the total weight of the beam and the water times it with the gravitational acceleration to find it. Up next, we're going to apply it to the static of equilibrium. For the moment, we use it use it to find the force applied on B, which is 10.18 Newton, and for the force that applied on A, we find it, which is 10.18 Newton. As you can see, we cut the beam into parts so that we can find out the forces applied onto V and the moments applied onto M. As you can see, on the second part of the beam, the maximum forces applied onto V is 10.18, and the maximum moment, which is M on the second part, is 1.425 Newton meters. Now, according to our previous calculation, the maximum of the moment is 1.425 meters. We use the maximum moment to get the moment of inertia, which is 2.8485 times 10 power of negative 9 meters to the power of 4. We use the moment of inertia to find the ultimate stress of the beam, which is 4.3 megapascal, and we use, since some safety factors is 1.5, we can find the reliable stress, which is 2.87 megapascal. Lastly, this table has stated the moment and the force that apply onto the beam when different loads that apply onto it during our experiments.
Let's moving on to the shear force diagram and the bending moment diagram. For the top graph is the shear force diagram, and the V is represent the shear force. As you can see, the shear force is zero at the beginning, at the initial overhang, and the shear force increase to positive 10.1 at Newton after passing through the right side of the first support, and remain constant until reach the center. Uh, with the presence of the log wedge and the spaghetti wedge at the center, the shear force dropped to negative 10.1 at Newton until the second support and becomes zero in the end. And for the bending moment diagram, the moment is zero at the overhang. When we move toward the first support, the moment increase linearly and reach the peak moment, which is 1.425 Newton per meter at the center.
Hi, my name is Yan Li, and now I want to present my part, which is conclusion. Based on experimental result, the bar could withstand a maximum load of 19.62 Newton. Through shear force and bending moment analysis, we determine maximum bending moment and calculate allowable normal stress by applying the safety factor of 1.5. From this bending test, we can understand the strength of the structure not just depend on material use, but it also depends on shape, form, and load applied on the structure. By comparing theoretical calculation and experimental result, we can gain a deeper understanding of why difference occur due to uncertainty and imperfections. For the reflection, our group learned about teamwork. We worked together when conducting the bending test and dividing tasks based on each member's strength. Next is communication. We maintain a clear and open communication to coordinate tasks and share ideas during the calculation part, which is the shear force and bending moment analysis. Lastly is problem solving. We overcome challenges together by using tape to make the bar reach the length required when model fabrication.
So that's all for our presentation. See you next time. Have a good day.